Welcome to This Explainer. Today, we are diving into a truly fascinating topic, renal scintigraphy. We're going to demystify exactly how we visualize and measure the highly complex, microscopic fluid dynamics of the human kidney. And the craziest part? We do it all in real time. So let's just jump right into this with a fundamental question. How do you actually film the inner workings of a human kidney in real time? I mean, think about the ultimate challenge here. We're trying to map an organ that literally never stops. It's constantly filtering, pumping, and reabsorbing fluid. It is this relentless biological factory, and figuring out how to capture that intricate motion, well, it's a pretty profound medical achievement. Here is our roadmap for today. We'll quickly cover the scope of scintigraphy, review kidney architecture, break down the math of urine, map our tracers, explore the protein-binding paradox, and then we'll wrap the whole thing up with a clinical decision guide. Let's get into it.
All right, Section 1, the scope of renal scintigraphy. Two distinct lenses.
When we look at our imaging toolkit, there's a really clear division of labor. First, we have dynamic renography. You can think of this as your live-action feed. It evaluates real-time physiological processes, stuff like measuring renal perfusion, quantifying differential function, and actually watching urinary tract obstructions as they happen. Then, on the other hand, we have cortical scintigraphy. This is much more like a high-resolution static photograph. Instead of watching fluid in motion, it looks at the static anatomy to identify structural damage, pinpoint acute pyelonephritis, or map out renal scarring. Both are absolutely crucial, but they serve entirely different diagnostic goals.
Moving to Section 2, architecture of the kidney, the biological factory itself.
Think of me as your tour guide here for a second. If we look at the macroscopic zones of the kidney, you can see exactly where specific tasks are delegated. On the outer edge, you've got the cortex, which acts as the main glomerular filtration zone. Deeper inside is the medulla, and that's the primary site for tubular secretion. Finally, the whole thing funnels down into the renal pelvis, which basically serves as the collecting system before transporting that fluid down the ureter. Scintigraphy targets these specific zones, depending entirely on what we need to see.
Now, zooming in from the whole kidney down to the micro level, the nephron, notice the intricate plumbing we're dealing with. We have the afferent arteriole bringing blood in, and the efferent arteriole taking it away from the glomerulus. But pay special attention to the juxtaglomerular cells and the macula densa. These are absolutely crucial. They are the pressure-regulating sensors of the entire circuit. The macula densa detects sodium levels and signals the JG cells to release renin, constantly adjusting the vascular pressure just to keep this filtration factory running smoothly.
Section 3, the math of urine. Let's quantify this fluid flow.
We can actually break this complex assembly line down into 4 logical sequential steps. Step 1 is the input, right? The raw blood flowing into the system. Step 2 is the filter, governed by the glomerular filtration rate. Step 3 is reclaim, where the body grabs back what it still needs through reabsorption. And step 4 is the final output, the actual urine. Keeping this simple 4-step sequence in mind makes the genuinely astonishing mathematical realities of urine formation make perfect sense.
And honestly, this brilliantly illustrates just how extreme the kidney's workload really is. At stage 1, the input, the system takes in a massive 1,200 milliliters of blood flow per minute. That is 20% of your entire cardiac output. But follow that flow down to stage 4, the final output. It's a mere 1 milliliter per minute of excreted urine. I mean, how does that happen? Well, at stage 3, as the ultrafiltrate travels through the tubules, the body reclaims roughly 99% of it. The sheer volume drop from 1,200 down to just 1 milliliter per minute is staggering. So the real question is, how do we actually measure this massive flow clinically? We rely on 2 core metrics. First up is effective renal plasma flow, or ERPF. Now, if a substance was extracted 100% on its very first pass, its clearance would equal total renal plasma flow. But here's the biological reality. Literally no clinical substance has a 100% extraction rate. Because of this, we measure effective renal plasma flow, which normally sits around 600 milliliters per minute. This ties directly into our second metric, the extraction fraction, or EF, which is simply the exact percentage of a tracer that gets removed from the renal plasma during a single pass.
Section 4. Mapping tracers to nephrons. It's time for some specialized tracking.
We don't just throw radioactive tracers into the bloodstream and hope for the best. We actually design them to exploit highly specific biological pathways. We have agents like TC99M-DTPA that exclusively target glomerular filtration, which is a process powered entirely by pressure differences. Then we have agents like MAG3 targeting tubular secretion, which relies on active transport by the cells. And for static imaging, we have tubular fixation tracers like DMSA that bind tightly right to the cortex. Every single tracer is basically a custom-fit key for a specific physiological lock.
Let's draw a hard contrast between those first two pathways. Glomerular agents are passive filters. They rely purely on the mechanical pressure pushing fluid through the glomerulus. They're just along for the ride. Tubular agents, on the other hand, are active secretors. This is an aggressive, energy-consuming process where the tubular cells actively pump the tracer out of the blood and into the urine. It is quite literally the difference between effortlessly floating down a lazy river versus actively rowing a boat against the current.
And here's how these two different mechanisms play out in clinical reality. TC99M DTPA is our clinical standard for measuring glomerular filtration rate because, well, it's simple, it's cheap, and it's freely filterable. But because it's only a passive filter, its extraction fraction is surprisingly low. We're talking less than 20%. But then you have TC99M MAG3, our modern standard for tubular secretion. Because it utilizes that aggressive, active pumping mechanism, it hits a much higher extraction ratio of about 0.4 to 0.6, and that gives us incredibly excellent image quality.
Then, of course, we have the morphologists. This is TC99M DMSA, our primary cortical fixator. Now, unlike the dynamic agents we just talked about, DMSA requires a deliberate 2 to 3 hour imaging delay. Why? Because we literally have to wait for the slow background clearance to happen in the body. But let me tell you, that wait pays off beautifully. Once it fixes to the proximal tubules, it gives us remarkably high target-to-background ratios. It remains the absolute gold standard for detecting acute pyelonephritis and mapping out structural renal scarring.
Section 5. The protein binding paradox. This is a fascinating medical mystery. Okay, I've got a question that might challenge your intuition here. How does high protein binding actually lead to a higher extraction fraction? Think about it for a second. If a drug is tightly bound to plasma proteins, it's physically blocked from being passively filtered through the glomerulus. It stands to reason that it should be much harder for the kidney to extract it, right? So how on earth do certain highly protein-bound agents get extracted so incredibly efficiently?
The answer to this paradox brilliantly illustrates a core physiological insight. Active transport overrides protein binding. Take the MAG3 paradox, for instance. MAG3 is extremely highly protein-bound, roughly 79 to 90%, and yet it achieves an extraction fraction of 40 to 50%. The answer lies in the sheer aggression of that active proximal tubular secretion we talked about. As the tiny fraction of free MAG3 is rapidly secreted, the chemical equilibrium in the blood suddenly shifts. To maintain that equilibrium, the remaining MAG3 is literally stripped away from the plasma proteins in real time, making it instantly available for active secretion. It is a stunning display of dynamic biological mechanics.
Section 6. The Clinical Decision Guide. Let's synthesize this into a practical playbook.
So, let's look at this master matrix to bring it all together. DTPA relies nearly 100% on glomerular filtration, has low protein binding, but a low extraction efficiency of less than 20%. MAG3, conversely, is almost entirely tubular secretion. It's highly protein-bound, but achieves a robust 40 to 50% extraction efficiency. DMSA, our cortical fixator, has high protein binding, but its extraction efficiency isn't calculated in the same dynamic way since it just statically binds to the tissue. And finally, I-131 heparan, which is an older standard, heavily relies on secretion and achieves the highest extraction efficiency of all, up to 87%, though it does come with some less favorable dosimetry.
When we compare the actual visual results of these pharmacological differences, the image quality varies wildly. MAG3 completely proves its superiority as a functional agent. You get an overwhelmingly high target-to-background ratio in incredibly sharp anatomical detail. Compare that to DTPA, which is somewhat limited by its low extraction fraction, or the older iodine agents, which often suffer from poor spatial resolution. The active secretion of MAG3 simply paints a much brighter, clearer picture of renal function.
So, applying all of this to a final decision tree is actually pretty straightforward. If you need to quantify a true glomerular filtration rate, you choose TC99M DTPA. If you need to quantify effective renal plasma flow, evaluate perfusion, or critically assess a urinary obstruction, your go-to is TC99M MAG3. If you need precise morphology to assess renal scarring or acute pyelonephritis, you choose the cortical fixator, TC99 DMSA. And importantly, if you just need to calculate relative or split renal function, any of these three agents can successfully get the job done based on their specific uptake mechanisms.
Which brings us to our final thought for this explainer. Mastering renal scintigraphy means truly mastering this beautiful, relentless physiological flow. We've seen how specific radioactive keys can unlock the secrets of glomerular filtration, tubular secretion, and cortical binding. And it leaves us with a pretty provocative question. If we can trace a single drop of plasma through a microscopic biological factory in real time, seamlessly overriding chemical paradoxes like protein binding along the way, what unseen machinery might we uncover next? Thanks for exploring the dynamic world of renal imaging with me. Catch you next time.